distributed generation and energy storage in a few more minutes because we're seeing a lot of people starting to hop on. So everyone's on mute right now, so just bear with us and we'll get started in a couple minutes. Okay. Our webinar series, Opportunities and Challenges of Integrating Wind, Solar, and Other Distributed Generation and Energy Storage. And we appreciate you taking time out to attend our webinar. And let's see, the webinar is an online session hosted by Peter Asmus from Pike Research, and it is going to be show how power management system solutions can help integrate the challenges from the power industry with distributed generation. So we're also going to show you the history and some of the future trends of the distributed generation technologies. So with that, questions can be sent in during the presentation and we will log them, or at the end of the presentation we'll be able to unmute you by raising your hand and we can have a discussion with our panelists. So with that, I'm going to go ahead and introduce Peter Asmus from Pike Research.
Thank you, John. Yes, my name, as you know, is Peter Asmus. I've been with Pike Research here for about 3 years, but been writing and analyzing energy trends for over 25 years with a specific focus on wind and solar technologies. And with Pike Research, I've been primarily focused on microgrids and virtual power plants, which are ways to aggregate different forms of distributed generation. So I'm going to introduce our 3 panelists. First, I want to introduce Rajan Chudgar from Power Analytics, who's the Vice President of Smart Grid. He joined Power Analytics after spending more than 15 years in the electricity market and utility business with a focus on software development, renewables generation, market strategy, and smart grid solutions. He started his career as a research engineer at ExxonMobil, was both a director of market redesign and a program director at the Electric Reliability Council of Texas. Served as manager, then as principal at global engineering consulting firm Black & Veatch, and was a manager at energy consulting firms Fortegra and the Structure Group. He holds 6 U.S. and 2 international patents. Next up, I'm going to introduce Bob Bellemare. He's the COO and managing director at Utilitipoint. He advises clients on asset valuation, financial modeling, strategic planning, public issues management, and pricing products and solutions. He previously worked for Fortune 500 utilities in a variety of capacities, including Managing Director of Energy Services, Director of Market Research, Wholesale Trading and Operations, Research and Development, Distributed Engineering, and Power Plant Engineering. His experience includes working on one of the largest coal plants in the Northeast, as well as helping to manage some of the largest solar and wind research projects of their time. And then James Waring is the executive chairman of Cleantech San Diego, a not-for-profit formed to stimulate the creation and expansion of a clean technology business cluster in the San Diego region. Prior to co-founding Cleantech San Diego, Waring worked for Mayor Jerry Sanders and the City of San Diego as Deputy Chief Operating Officer for Land Use and Economic Development. He currently serves as a mayor's appointment to the San Diego Housing Commission. In 2012, Waring was appointed to the California Transportation Commission by California Governor Jerry Brown. So those are the panelists today. I think we're going to get going here. Let's just kind of go over the topics we're going to cover. We're going to start with an overview of distributed generation. Why to use distributed generation, and then we're going to also talk about the benefits and applications, some future initiatives, and then we're going to draw some conclusions. So without further ado, I think we're going to go through an introduction here with Raj, I believe.
Okay, so this introduction is based on an IEEE paper that was presented at the PES General Session a few weeks ago in San Diego. And as you can see, most people in the world today view electricity as a commodity. So it's similar to gas, water, telephone, and they don't pay attention to their electric bill until there's a problem with it. So when there's a spike in their utility bill, or they're paying a lot more, then they start realizing, I need to do something to take care of the problem. So that's pretty much the introduction of what we're going to do. So we're going to go ahead and tackle what distributed generation is. So the electric industry was one of the first industries to embrace computer technology to increase the reliability of the grid. They use automation and centralization and provide reduction in response times. And what this did was gave them the economies of scale for bulk generation and transmission. So what that did was lower the cost of electricity to the end users. So it didn't matter if it was residential or commercial or industrial. But one thing that it did do was you have to monitor thousands of data points to be able to distribute the generation through your transmission and distribution lines. And that was a major challenge for them. So the other thing that the utilities have done a very good job on is providing power with up to 99% uptime. So there's very little blackouts, especially in the U.S. Okay. So what is distributed generation? Because up to now, everything's been a centralized power plant. And if you go back to the vision of Edison, the initial plants were direct current. So they were all localized power plants. Okay, the centralized power came about because of alternating current, and the transmission and line losses for DC current was too big to do the centralized plants. So initially, the vision was to have a lot of small plants located close to the customer loads. And that is exactly what distributed generation is that's being embraced today. So some of the things that you can do are put the distributed generation near the customer loads at substations, and this allows the utility to deliver power to customers that are far away from a transmission and distribution line, that they don't have to build an infrastructure to go ahead and get the power out to those end users. Some of the technologies that are being used, we'll go into that in a little more detail later, but it's gas turbines, storage systems, wind turbines, and one of the key things about distributed generation is the installed cost of the distributed generation capacity is not that much. But the problem is they're out in the middle of the desert, or the wind farms are offshore. How are you going to get that power into the grid? So when you take into account the transmission and distribution infrastructure, distributed generation is a little bit more costly today, but hopefully in the future, we'll show you the future trends on how we can implement that where it's very cost effective. Okay, the current model for electricity generation is the centralized power plant, and that is coal, oil, or natural gas, and nuclear. Nuclear is about 20% of our generating capacity in the U.S. today. So that's how it's done today. And like I said on the previous slide, the centralized power models require that transmission and distribution grid from the center to outlying customers. So it could be tens to hundreds of miles of your high voltage cabling going out to get the power out to the cities and factories. So some of the problems that you have with that centralized system are the transmission distance issues. You do have some line losses. It's fairly low at the high voltage levels. Coal has high greenhouse gas emissions. Nuclear has your nuclear waste problems. The lengthy transmission line losses. Environmental distribution where the lines are constructed, because you have to build the lines through forests and land. And then you have your security related issues that go along with that. So that's part of the history, okay? And then what distributed generation does is it eliminates a lot of those issues with the centralized power plants. So by locating the source near the end user, you don't have your long line losses, you don't have your transmission and distribution, you eliminate a lot of your security problems, okay? And for example, solar panels is a really great example of distributed generation because they could be standalone units or integrated into an existing energy grid. So it's a win-win for the utility and the end user. And this came from a European Energy Commission study, this slide where it shows what we thought the central power stations are today, they're calling it yesterday, and the distributed generation for tomorrow. So Europe is starting to embrace this technology and idea of distributed generation. So I think this is a great graphic showing what it is today or yesterday and where we think the future is going to be heading with distributed generation. Okay, and with that, I'm going to turn it over to Bob for the different types of distributed generation.
Thank you. This is Bob Bellemare, and welcome everybody to the webinar. Appreciate your participation. This is just an overview. You're probably familiar with many of these generation types, but under the distributed generation umbrella, there are several technologies that most consider to be part of that picture. They start with what I would call conventional type generators, from diesel engines and generators, which can range from a relatively small size of around 50 kilowatts on up. Here they show 6 million watts as the upper range, but of course it can be even higher than that. And they're used mainly in standby mode for customers who need full backup or partial backup of critical type things such as hospitals and the like. So largely a commercial industrial application. You have natural gas reciprocating engines, smaller type, again, of generators, and primarily used, again, for backup or peaking power. In other words, they can contribute towards those times when the utility system is highly constrained and in need of new generation or generation resources, even at the end of the power system. Natural gas combustion turbines, which are literally turbines that are fired by natural gas, and their size is from a half a megawatt or 500 kilowatts on up to 30 million watts per megawatts. But they can go even higher, if you add multiple units and the like. So these tend to be for commercial and industrial, especially industrial, and where, as you see on the right, where you combine it with using some of the heat that's produced to run other processes such as heating and air conditioning, as well as you can add on to it what's called a steam cycle to create very efficient combined cycle or combined heat type of applications where you can push the overall efficiency up to 50%, 60% or higher from energy in to useful energy out. And we have an example of that coming up. So these tend to be, those larger applications tend to be for industrial or university type settings where you can take advantage of some of the heat that's produced. Microturbines were all the rage, I guess, about 10 years ago. You know, those are compact units, usually run on natural gas, and you can see they're smaller in size, but 21 to 33% type efficiency. And then fuel cells, which are used for premium power, they tend to run 24/7, and they range from very small to modest size, like 3 megawatts. Photovoltaics or solar, you know, tend to be small in size, on up to about 100 kilowatts, although you're seeing some larger applications now where space allows, but that's one of the key considerations with photovoltaics. What's not listed here, too, I know of some small-scale wind that can be, you know, at a site-specific location, and those can be kilowatts to 100 kilowatt type of applications, although most people think of wind as being large, applied in large wind farms. And as a prior speaker was saying, you know, they tend to be, unfortunately for wind, can oftentimes be in remote locations, and so you have issues of how to interconnect wind. And that's true. What we're trying to point out here is some of the challenges with distributed generation are certainly location-specific, both in terms of resource, which you have available to you, your own needs and requirements, as well as each state and each utility will be different in terms of how you interconnect and the economics of what they provide for incentives and the like. So you get very situation-specific, and there's no one answer, I think, that applies to all. And these are just some examples of the technologies which you're probably familiar with, the wind turbines. These are larger scale type wind turbines up in Tennessee, and photovoltaic, where this is a solar panel, which can be roof-mounted or ground-mounted, depending on what you have available to you. In this application, this is showing a university application in California where they took advantage of the combined cycle or combined heat that I was talking about earlier. What happens here is they supply, I believe, most or if not all of their energy needs, electrical energy needs, as well as their chilled water for the university through this application. I've been involved in several of these types of situations with universities and industrial customers where you have a good electrical energy need match with some of their other uses. They could use the heat and energy produced by the creation of electricity itself. And you know, there's a lot of capital involved and a lot of intricacies there as to how you make everything balance out. But they are an application, and they've proven to be highly efficient and very economic in many situations. And this is just an illustrative diagram of gas turbines. You know, that the gas is used to fire the turbine. And what this doesn't show is then on the back end, you can use that exhaust to run a steam cycle, what we call a steam cycle, and then you can further use the resulting heat to run other processes like chillers and heating systems. So why use distributed generation? And I believe our analysts will cover this topic here.
Okay, so many customers have this diversified electrical equipment, and they want the distributed generations, so they're closer to the source with solar, wind, or storage that gives them additional capacity, and they eliminate some of the constraints from the utility. All right. The other nice thing is with the large availability of natural gas that we're able to use small gas turbines locally to offset the electrical rate structures, where you can choose when you want to run your on-site generation capacity to prevent some of the penalties with your electrical rates. And there's regulatory incentives to do distributed generation to work with them, and we'll get into some of those regulations later, but that's a fairly large challenge because each state is slightly different. But in order to manage all these different generation sources, you need to be able to centrally manage the power system. Okay, so you need an electrical power management system software package, and this is an example that we have at University of California, San Diego at their microgrid. And you can see it has solar panels, it has diesel generators, it has a CHP plant, and it shows all the generation capacity and all the loads, and it allows you to analyze if the utility goes away, will my generation capacity on site be able to manage my loads, or do I need to strip some loads, keep things running? And this is a fairly significant challenge for distributed generation because there's a lot of different vendors involved and communication protocols. So you're going to need to be able to have a dashboard of your equipment and make it easy to integrate as a single system. So this is the very first page of the dashboard of the UCSD microgrid, and it has a lot of distributed generation on campus. It's about 45 megawatts of generating capacity, and you can see it has, you can put anything you want on this because it's a web-based browser. You can have your weather, you do an analysis of your energy usage, and you can display that. So different people have different needs inside of your facility. So they can actually get different reports from this data. So as long as the data is coming in, you can slice and dice it any way you need. But it's a single point of integration showing the entire system. Okay, so the next thing that we're going to cover is benefits and applications of distributed generation. So with that, I'm going to turn it back over to Bob to go over the benefits of distributed generation.
Thanks. So my experience with this issue, working at both the utility and customer side, is that there's a lot of potential benefits of distributed generation. Of course, it comes down to those benefits and costs, and there's over one of the things I always like to point out. We'll talk a little bit about later on. There's over 3,000 electric utilities in the United States, and they all have different characteristics, and they all have different needs and different incentives, ranging from none not to many. So it really gets down to site-specific issues. And some of the benefits that are well recognized, I think, on the by all parties, is that you can lower transmission and distribution costs. We have to invest a lot in the wires for the peak demand, and it's a relatively inefficient system because we at least so far, haven't found a way to cost-effectively store electricity. And so anything we can do on the demand end can help in bringing about lower investment in the wires, which are very expensive, and frankly, people just don't like to see them. So transmission is one of the hardest things to build in this country right now because people are really don't like to look at transmission lines. And so anytime you try to put in a transmission project, you have a lot of issues that you have to work through with the communities. So, transmission and distribution are some of the benefits that utilities have seen, especially with certain types of technologies on distributed generation, and things like the combined cycle that I mentioned, which, they don't have variability in their fuel supply, if you want to think of it like solar and wind, although solar sometimes can correlate very nicely with peak demands, depending on your location. They can help increase reliability, depending on how they're integrated and the type of technologies you choose. So someone made the comment earlier that the electric grid is typically 99.9%, sometimes 99.99% reliable. That's not good enough for some customers, and so you have to look at going even beyond that, and that normally speaks to putting in some solution at the end of the system at the customer point. There's a lot of companies now that are looking at their sustainability and impacts on emissions. And so for some, this is not about necessarily least cost design, but also about adding into the environmental equation the way they want to talk about themselves and their objectives as a business. And so many of these technologies do lower or eliminate emissions in a significant way. And so I have seen customers taking it on for those reasons as well. Improved power quality ties to reliability issue. You know, there are customers with that high reliability and power quality need. And to the point that was being made earlier, some companies and customers maybe don't take full advantage of the economics here, where you can use your resource to what we call peak shaving in the industry, or help contribute towards those crunch times, such as what California experienced years ago when they had that shortage and prices got extremely high. And a lot of the payback, or some of the payback anyway, for these systems can be in those crunch times, which may take years actually, because we don't normally experience those kind of crunches every year. So you have to be on top of your game in order to take full advantage. And frankly, the markets are evolving on this. We, as an industry, have really designed many of our market mechanisms, as well as our engineering designs, for what I like to say is one-way power flow. You know, power from the central plant down to customers. And now we're starting to add this end use, or the end component to it. So a lot of work still needs to be done on our market structures, but they're under development, especially in advanced markets like you see in California and in the Northeast. Since some of these run on gas, natural gas, the point here is that if you have a natural gas supply that's in a good location with reasonable prices, you can, in some markets, arbitrage natural gas prices against electricity prices. And again, this takes a level of sophistication and tools that you would need in order to understand the nitty-gritty details of the economics, which will be location specific. But this is where you can see some large economic gains, depending on where you are and depending on what natural gas prices are doing, which have a lot of volatility to them, so the opportunities do change seasonally as well as year to year. This chart shows some of the benefits that were captured in a DOE report, and we basically have gone over most of these already. One of the things that's not captured here but is a developing market is in some states you have renewable energy credits that you can take advantage of if you're using renewable generation, and each market is different on that. So again, location specific, but in addition to some of these system benefits and direct economic benefits, there are some other markets developing around renewable energy credits and the like. So, the market is, at least in North America, is the sweet spot right now tends to be in the commercial and small and medium-sized industrial customers. In certain states, you have programs that are aggressive, even down to the residential level. Many of the largest industrials have already embraced whatever is cost-effective for their on-site power. But you do see, like in the case of the university that was mentioned earlier, new applications of some large-scale generation at the large industrial or large commercial type customers. I already mentioned residential units. We are starting to see inroads down into that level of market, especially with roof-mounted photovoltaics and some small-scale wind, depending on, again, your location. And we've already talked about many of these applications that are common: combined heat and power, peak shaving, premium power, and again, for those looking to reduce their emission footprint. The thing I always like to point out, and I've mentioned it several times here, are incentives. And this is an example of a study we recently did for one of the DG, distributed generation manufacturers, who wanted us to look at the electric cooperative market in a certain geographic region in the United States. And what you find are a wide variety of incentives, and these incentives do change almost daily, so you have to really stay up on it. But a variety of incentives you will find, such as property tax reductions or exemptions, like they won't include that in the property tax valuation, so you get a tax break by installing some of these equipment. You see things like sales tax exemptions on the installation costs or certain parts of them, income tax credits, which are state and federal, of course, and production tax credits, which the most famous one right now is wind. Wind's production tax credit expires this year, and if it doesn't get renewed at the federal level, that will have a significant impact on the wind industry next year and beyond. Of course, loans are available, ranging from low to no interest type of loans. And then you have a wide range of utility rate structures, and they can be quite complex. And so, depending on your situation, the rate structures alone can take quite a while to understand. Some are what we call net metering, where the electricity production is simply netted against your electric use. Others have separate metering for the generation compared to the actual use of electricity, and the utilities will give you different credits for the generation compared to what they sell you electricity for. And that can be quite complex to those unfamiliar to the industry as to why. It doesn't seem sensible to many. You're selling to me at 10 cents a kilowatt hour, but you're only providing me a 5 cent a kilowatt hour credit. And that depends on the technology and issues that the utility incurs, because they still have to build the infrastructure to serve you or maybe back you up for whenever that generator may not be available. So there's quite a range of incentives and ways of metering that you have to dig into. And in this example, there were 50 utilities, larger utilities that we examined. 38 of them had well-defined what we call interconnection requirements, what you have to do to actually interconnect the generator and the process there and the metering and those types of things. But interestingly, even with all this activity, there were 14 utilities that we couldn't find a policy on or any well-articulated interconnection standards. It's like call us and we'll tell you. Another thing that can be important is checking into building and local codes for certain technologies like wind and solar. You can run into some local codes and requirements that you may not be expecting. So those are things that have to be well thought out and well investigated before jumping into this. Next slide. This is just an example of the variations of AUC. This relates to the study I was mentioning in the prior slide. When we looked at the states, you see this variation in 5 to 6 incentives, and you see those in the big circles, and then you see intermediate, and then you see some states with no incentives whatsoever, at least for this particular technology we were examining. So again, just to emphasize the point on the variation that you see on incentives, interconnections, and standards and the like.
Okay, so that was a pretty good overview of the distributed generation, but then how do you take this and apply it? So I wanted to just touch base on one of the applications, and we're just going to touch on solar briefly with the Sunshot Initiative from the U.S. Department of Energy. And this is a nationwide initiative that wants to reduce the installed cost of solar energy by 75%. Because right now, the cost per kilowatt hour of solar is dramatically higher than other sources. So we're doing a lot of this research with the University of California, San Diego. And here's a graphic of what it would look like. So UCSD has a microgrid, and it's a sophisticated monitoring network that integrates their high penetration PV into the microgrid. And so we're able to gather the information and do an analysis of what the PV generation capacity is. And one important factor there is the weather, cloud cover. So if we look at the cloud cover, they actually came up with a sky imager. So there's a couple of things they can look at. They look at the existing conditions, and they also look at the forecast going out at least 24 hours to calculate what the power generation will be. And that's a big deal when it comes to PV generation. So in order to do that, as we touched on earlier, you need a sophisticated software package to integrate that in as one system so that operators can make adjustments to their microgrid as required based on cloud cover or bringing other loads and generation capacity online. Okay, so the future initiatives, I'm going to turn that over to Jim Waring, and he'll go through this with the group.
Okay, thank you. My pleasure to join and add to some of the comments of my colleagues. I just want to start to emphasize what we're seeing here in California and in San Diego. And it's really become evident recently. We have a very progressive utility, very engaged in the community in trying to experiment with and take a leadership role in distributed generation. But at the end of the day, what everyone has to recognize is that the utilities feel an enormous pressure to deliver reliable, affordable power 24/7, 365. And we're seeing on each of these initiatives that we work on, each of the ideas, each of the programs, they automatically come back to that mandate that the utilities feel. And I'll give you a great example of how real it is. Last September, we had a blackout caused by a switch problem in Arizona. I think it lasted 12 or 16 hours. The utility was hit by an amazing number of lawsuits by people that said they lost food that was in their refrigerators. Their businesses were interrupted. And I'm not sure how those lawsuits were resolved. That's really not the point. The point is that the public has an expectation of electricity as a right, on demand and a good cost. So each of these subtleties really come into play. The other thing that we're seeing that I don't think can be emphasized enough is that your reduction of energy usage is really the best and most easily monetized application. In other words, if you or your clients are able to reduce the energy demand by 3, 4, 5, 6%, that has an immediate and very positive return to everyone involved. So the other thing, as a general principle we're seeing, and I'll get into this on some of the later slides, is that the closer you can build your distributed generation or acquire your distributed generation power, the closer to the use, the better. There's been a lot of discussion about the UCSD microgrid. That is on campus. That is islandable. And the further you get from an islandable system, the more issues will come up that I'll touch upon in another slide. The next slide just talks about U.S. renewable resources and some of the constraints, and I want to emphasize land use. What we are seeing here in California, and I read enough to know it's happening all over the country, is there is this conflict between people's stated goals of renewable energy and clean energy and the fact that no matter what we're building, it has to go someplace. In San Diego, tomorrow, there is a hearing at our County Board of Supervisors regarding a wind project in East County. And that's the first of a series of projects that in the aggregate will be about 400 megawatts of power. So they're a series of projects. Very sensitive land use issues. Then as we come closer in, even projects that are smaller, sort of I'll call micro utility scale, 10 to 20 acre solar projects, there are also land use problems. So the ability of people to accept, and these smaller ones would be solar in their neighborhoods, becomes a very important local and ultimately political issue. The next slide just talks about the technology potential. I will say from what we see at Cleantech San Diego, and again, we are a policy shop and a market development shop, that the capacity of the industry to produce and deliver distributed generation exceeds the ability of the marketplace to accept it. And again, some of the reasons for that have been touched upon in terms of incentives and the complexities throughout the different states. The next slide, which I'm trying to get to. So let me just speak to the again, some of the things that we're seeing here. We have in San Diego, there are approximately 1% of our rooftops have solar. So that's actually a small amount, but it is growing, and it's creating some important policy issues that are being studied by the California Public Utility Commission that will have important consequences to all of the distributed generation, non-islandable distributed generation. And that is because these systems do require the grid. They do require transmission. Again, during the blackout, many people that had rooftop solar were surprised that their solar didn't work. They weren't sensitive to the fact that their solar only worked in connection with the transmission grid. And that's because, to date, we don't have affordable behind-the-meter storage. Therefore, even if you have a net zero meter, you are still utilizing the grid. Maybe it's the distribution and not the transmission session, but you're still using it. Now, that's creating an issue, and that is if I have a rooftop solar that is net metered to zero, so I'm not paying anything, but I'm still using the transmission system, who is paying for that? Where does that subsidy come from? Now, under our current rate structure, that comes from everybody else. And again, at 1% penetration, it's not significant, but it will become significant over time. So we're having a bit of a policy and political debate about how much should rooftop solar, a distributed generation, local produced, pay for the use of the transmission line. And this is going to have very significant impact and tying in even to larger scale. So the utility is trying to do a program called Share the Sun, and they have a filing with the California Public Utility Commission for Share the Sun. And think of that as a fractional interest in a 10-megawatt solar project someplace in basin. You live in an apartment, you have a building that can't accept rooftop solar, whatever the case might be, so you would buy a fractional share of this power. Well, how should that be? What should your benefit be? All of which goes back to monetizing. From a consumer point of view, you would like to have that be a virtual net meter. In other words, you'd like to reverse your meter and shave off the top power. The utility's position is no, there should be a feed-in tariff that is just a slight premium over the actual cost of power. And they're talking about 10 to 11 cents a kilowatt hour as this feed-in tariff, what makes it almost impossible to monetize these systems. So we have this tension between a stated goal of encouraging in-basin, distributed, small-scale generation of primarily solar power. That's the stated goal. But how do you monetize that? And a lot of it does come back to the cost, the other costs on your bill. SDG&E says that its blended cost of producing a kilowatt of power is roughly 7 cents. And that number's come down significantly because of natural gas, but 7 cents. Then you're going to have an average bill of 20, 21, 22 cents. I mean, there's a lot of different payment rates. But as you can see, there's a gap there of 14 cents that they say goes into transmission and other costs. How that is captured and carved out as a benefit for people with either rooftop or with remote solar production will be key to the development of the sector. So again, we talked now. The next slide is about industry need. I still go back to what I said before. I think the industry is ahead of the regulatory system. As it's been pointed out by, I think, every speaker, it's very complicated. We have hundreds of utilities. We have 50 states and other territories. So coming up, understanding your local regulatory scheme, the incentives, some of these things that I just alluded to, whether you're going to have a feed-in tariff or a virtual net meter, are absolutely critical to knowing how, whether your company or your clients are able to monetize these systems. The next one is just a really cool map showing the future of electricity production, and you'll notice the difference primarily in Africa. And I think one of the things this points out is that the future of distributed generation is almost unlimited. And there'll be many, many parts of the world that will never have a grid, will never have these issues that I just alluded to, where the utility has this huge legacy cost in transmission that it needs to monetize. In the future, just like our cell phones, there are areas of the world that will never have wired phones. Well, there'll be microgrids spread out around the world, which will create enormous opportunities going forward. So that's kind of a quick rifle shot of that, and now I'll turn it back for conclusion.
Okay, the conclusions. So what did we really find here? It's the reality is distributed generation will maximize uptime through islanding techniques, which we've discussed throughout the presentation. The current cost of distributed generation will eventually come down, but today, since location is the key factor for success of distributed generation, the transmission and distribution capability is not in place to get to the wind and the high penetration PV that's located throughout the country. So distributed generation costs will come down. That's what we think, okay? And then the policy and the different states' governments are going to be a key issue in implementing distributed generation. So Jim touched on that during his part of the presentation. If you have questions on that, we'd be glad to take them here in a couple minutes. And the regulations do vary by state and region. So the U.S. grid is over 1 terawatt, and distributed generation is not going to solve this issue, but it's definitely going to be a part of the future. So it is going to be important research for electric utilities, and we see this as an important aspect going for an effective energy strategy for the country. And that's going to include the power companies, the end users, and how they're going to integrate this on the load side of the meter and the utility side of the meter. But one key factor that we touched on many times is you have to have a power management system solution that you can monitor the entire package of all your distributed generation and how it integrates into the grid, or you're not going to be successful. So that power management solution that we showed you is a key point of what we want to go over. And this is the second of a series of 4 webinars. The first one is how do you integrate multiple systems together, and that was pretty well received, so that is still available as a download. This webinar is the utility integration, and it will be available as a download through the Stratech website. And the next 2 are listed up here, and so there's one in about a month on mission critical applications, and then the last one will be specifically on microgrid strategies. So with that, I'm going to turn it over to Peter,
Thank you, John. You know, I guess one question that came to my mind as I was listening to all this, and of course a lot of my research is focused on microgrids, is I was just wondering if, in terms of some of the panelists, how high can we go with distributed generation? I'm just wondering if folks have done any thinking of that. You know, I know someone, and some of you may know former PG&E expert Carl Weinberg, who was doing a lot of the cutting-edge distributed generation research at PG&E before they sort of dismantled their R&D program with restructuring, once told me he thought we could get to 40% DG, but that was the most we could go. And I'm just wondering if any other panelists have any opinions, and I would assume, you know, if you're going to get that high, you're going to need things like microgrids and virtual power plants. But anyone out there have any opinions about how high can we go with DG?
Sure. This is Bob. In fact, some of you might have caught last night or yesterday, Xcel Energy in Colorado had a moment where they were supplying 57% of their electricity from wind, which was a record-setting watermark as far as we know, in North America especially. Now, that was off-peak and there were certain conditions. So the answer is always it depends. I mean, I've been involved in this from a technical level in my career, and generally, depending on how your grid is designed and operated, because it was always, as I mentioned earlier, the system's developed assuming one-way power flow, and you have rural versus urban and all other kinds of characteristics you have to take into account. But most people on the utility side, anyway, if you were to ask them, say, depending on their configuration, they can handle 5 to 30% of electricity coming from the distribution end of the system without major modification or other major costs that would have to be incurred. Comfortably, most utilities would probably tell you somewhere in the 5 to 15% range, but some can push it to 30%, depending again on the system configuration, how it's managed, and other tools. You do have this, you know, companies like Xcel Energy really taking a leadership role on advancing the models, and because they have such a large scale amount of wind right now coming into their system. So this is certainly under development, but that's been typically what you hear in the industry, again, depending on the design and configuration of the local system.
Sure. That makes sense. And actually, there are parts of the German grid that have been up to 100% wind and solar already, although those are just, you know, short moments, and obviously that's been an issue. I think we had a question, and we can throw this out about maybe one more time revisiting, you know, the differences between distributed generation and conventional generation. And obviously, there's scale in fuel. I mean, even with wind, for example, one could argue that large wind farms are just like another centralized plant, I suppose, except it's a renewable fuel. But would anyone want to, one more time, try to succinctly sum up what's the difference, DG versus what someone might call, I guess, conventional or wholesale generation?
Sure. The industry definition would be conventional generation. It's something that we directly control and can manage the power production of. So normally it runs on a conventional fuel like natural gas or coal, hydro. Those types of things are considered conventional. And from an engineering operations viewpoint, we'd like that stuff because we can directly manage it. When you get into variable resources like wind and solar, it changes the way you operate the system. So those would be considered non-conventional and oftentimes distributed because they aren't typically located at the central power plant, although wind, you can argue, oftentimes is because they build out large wind farms that are connected to the transmission system. But what, from the utility lens, the challenge with wind and solar when you get into large concentrations of it is what you have to design and change your operations around. It's for, like, you know, when wind can go from full speed to zero, let's say, in a matter of seconds, how is your system going to manage that kind of dynamic? We don't experience those dynamics in what we call conventional generation, at least not in the same way. And then with solar, cloud passage causes issues. If you have a high concentration of solar at the what we call distribution end of the business, it can create some uneven situations. If you can imagine a cloud passing over and power production going from a high point to near zero. So these are some of the challenges we have with these alternate forms of generation. And again, it goes back to that 5 to 30%, maybe 40% levels we were talking about a minute ago, as to where, what level do you reach where it starts becoming, some issues you have to really deal with on the design and operational viewpoint.
Sure. Well, we're almost out of time here, but one final question, and I guess we'll try to keep our answers succinct, is what are the largest impediments to distributed generation, and how long will it take to get those impediments overcome? I guess one could view it as either technology, policy, or perhaps even other resources. We haven't talked about demand response, EVs. There's a lot of talk about electric vehicles even helping out on this. So does anyone want to grab that? What are the biggest impediments, and how long will it take to overcome those impediments?
Well, this is Jim Waring. Let me take a quick shot. Since this industry started to evolve, one of the big things that happened is the natural gas and fracking and the discussions and the opportunity to get large supplies of relatively cheap natural gas. And that's changed the whole economic structure and some might argue the need. So to me, natural gas pricing from a competitive point of view hangs over the entire industry or the entire opportunity. And the other thing gets back, again, remember that this is a consumer product that people rely upon. And therefore, you have these significant legacy investments that need to be maintained so you have redundancy in the system so that when you have periodic power outages from a renewable source, these direct on-demand fire-up instantly things kick in. So all of that changes the numbers. So I think that as any industry throughout history has matured, the economics become very important. And as this whole industry matures, I would say the overall economics and the overall policy aspects will become really, really important, very refined, and solving those will be where the opportunities will be created.
Very good.
I agree. Absolutely. The natural gas market has really changed the economics. At these low prices, it makes it a challenge. But natural gas, from my involvement, it will always turn on you. If you think they're going to be low forever, next thing you know, they're high. And then prices are high, and you think they'll never be lower, and they go low. So that's one of the big challenges, because you're normally playing against natural gas economics. But at the same time, a lot of these technologies have really come down in cost. And, at least half, I think, in the last 10 to 15 years, the price has been cut on things like wind and solar. So, there's a lot going on the cost side. But, yeah, in a lot of parts of the country, you're going to be hitting up against natural gas economics.
Yeah, no, I agree with the natural gas, although I do see most people are projecting, even with grid parity for solar, is within the next few years in a lot of key markets, and including Europe. So, I mean, there is progress. Unfortunately, the price that solar is competing against keeps going down. But as you mentioned, the volatility, that's the one advantage of the renewables is, especially wind and solar without any fuel costs. So there is that hedging benefit. And we are seeing industries, even remote mines, for example, now looking to solar that would have never thought about it a few years ago. But considering diesel, so natural gas is low, but you mentioned the developing world, we see one of the biggest markets overall for DG, especially renewables, will be the developing world, where they can actually compete with diesel in some ways, even without any subsidies, so you don't have to worry about production tax credits.
Absolutely. Again, it gets back to where you have the ability to island, the opportunities are unlimited.
I think the other thing we overlook a lot of times, because I'm working with customers on these issues, a lot of times, even when it's economic, the electric bill could be like the third operating expense in their business. So even though it can be economic, it can be very challenging to think that's the best place to deploy your capital when you have other opportunities, let's say, for that capital. So what happens in our world, in our little world, we think, wow, we can save you, 10, 15%, 20%, whatever it is. But still, that doesn't meet the hurdle rate internally for the deployment of capital to that situation. And sometimes you have a cultural issue or a structural issue where facility managers are different from those who make the buying decisions on these issues, and you got those types of things you have to deal with. So challenges all around, I guess.
Yes, I think we're out of time here, so I believe we have to go. John, I assume that's so.
Yeah, and we did have several more questions come in, but there was one general theme of where people wanted to get a copy of this PowerPoint. So we will follow up with everyone that registered with instructions on how to download this from our website.
Okay. Very good. And with that, I guess we're wrapping it up then.
Yep. Thank you everyone for participating, and
okay.
Have a great rest of the day.
Okay. All right.
Thank you.
Thank you.
Just change this and say, and for all you people are done. You just all got kicked off. So that was nice.
Pretty good winging it.
Yeah. Wow.